Okay guys, so in this video we're going to talk about calculus in polar coordinates. Now, just like parametric equations, the reason why we're dealing with polar coordinates is because sometimes it's just easier to write an equation in polar coordinates rather than in our rectangular coordinate system x's and y's. Often these equations are things that are circular curves of some sort, but it's not only those, but they generally have nice curves to them. And the idea here is that if they're already in polar coordinates, or if it's easier to think about them in polar coordinates, then it's probably easier also to derive or integrate or do kind of calculus with them in those terms rather than in terms of x's and y's. Okay, so let's start with areas here. So first of all, as a reminder, the area of a circular sector is given by this formula, A equals 1/2 r squared theta, where theta is in radians. Okay, so basically, we're going to use that same concept when we're talking about our areas of these polar regions. So essentially, our area here is the integral from a to b, 1/2 r squared d theta. So with respect to theta, where r is our f of theta, some function in terms of theta. So the idea here is that what we're doing is we're going to take a slice from that is radius up to this like f of theta. That's how long this radius is. And we're going to do it for every point along that curve from our A to B. So if you think about it, we take this and then we keep taking slices as we sweep along this curve here until we get to B. And that is what our integral here is. And that makes sense. I mean, that follows nicely. Okay, so let's start with an example. Find the area of a region bound by the curve and the x-axis. So we have some r is square root ln theta. We go from 1 to 2 pi. So let's go ahead and graph this thing. So r equals ln square root ln theta. All right, and we're going to take this, so this is what that curve looks like. We're going to take this from 1 to 2 pi. 1, there we go. So we're dealing with this thing. Now, we have it in rectangular coordinates, but we could change this over to polar if we want. It looks a little bit nicer maybe, or it doesn't. Who cares? All right. So let's go ahead and snip this thing and drag it into our Okay, it's a little bit big. So we are trying to find this region here, which is essentially kind of that. Okay, so the idea here again is we're going to integrate this thing from 1 to 2 pi of 1/2 r squared. Now our radius is just that. So it's square root ln theta squared d theta. Okay, so when we're talking about something like this, then we want to first simplify this a little bit. Squared and square root cancel, but not fully cancel, because if you recall, one of the definitions for absolute value of x can actually be defined as this thing is equal to the square root of x squared. This is actually one of the definitions of absolute value. So when you take the square root of a squared, it's actually going to be an absolute value. But it doesn't actually matter for our case, and I'll show you that in just a sec. We have the integral from 1 to 2 pi of 1/2 natural log theta. We do not need the absolute values here, even though technically it does, because natural log is greater than 0 for all x's greater than 1. So if we take a look at ln, okay, it is negative at some of these times, but from 1 onwards, the points that we care about, it is only positive. Again, if we take a look at it compared to this, these two functions are the same on the interval we care about. Okay, so just something to note. That's why I don't have absolute value here. Okay. So we're going to integrate this thing. I'm going to pull that 1/2 out, integral 1 to 2 pi natural log theta d theta. Now I don't know what the integral of ln theta is off the top of my head. This is going to be derived via integration by parts, so uv minus the integral v du. So our u here is going to be natural log theta. That means that du is going to be 1 over theta d theta. Our dv is going to be just d theta, and so then our v is going to be theta. All right, so plugging this in, we have 1/2 times uv. Our u is natural log theta. Our v is theta, minus the integral of v du. So theta 1 over theta d theta. All right, so that means we have 1/2 times theta natural log theta minus, these just become 1. So it's minus 1/2 theta. And we're going to take this from 2 pi to 1. All right, so taking a look at this thing, plugging in 2 pi, we get 1/2 times 2 pi times natural log of 2 pi minus 1/2 times 2 pi. Then we're going to say minus. And we have plugging in 1. Natural log of 1 is 0, so that term's gone. And we have negative 1/2 times 1. Okay, so we'll clean this up a little bit. These cancel, and we're left with pi natural log 2 pi minus pi plus 1/2. And this is our area. Now, as a reminder, if you're ever not really sure, you can obviously check your integration. So pi natural log 2 pi minus pi plus 1/2 is 3.1 whatever. And if we go to our functions, and we go over to the integral here, oops, should have done that here. So we go to our integral, and we're going to take it from 1 to 2 pi of our 1/2 times our square root ln theta, well, I'll just call it x to make my life easier, squared dx. And it's the same value. So that's good, that checks out. It's something worth noting. So we are correct here. That is our area. And again, it's approximately 3.13. Okay, let's take a look at another one. Find the area of the region bound by the curve of r squared equals sine 2 theta. Okay, let's start by graphing this thing. We can't do r squared in Desmos, so we're just going to call it r equals sine 2 theta. And then we're just going to take the square root of it. No. Probably should have just done the square root ahead of time. There we go. So something like this. This is the positive version. We also need the negative version, but if you look, r equals negative, it doesn't change it. So it is just this region here. So we're good there. So it's just the positive one or the negative one, doesn't matter. So here is our r, sine 2 theta. And so we want to know the area of this area or this region bound by the curve. So we're looking for this one and this one. Now, if we were to integrate this thing here and double it, then that would be the same. So if we take this region here and we doubled it, we could get this region as well. So, I mean, really there's no need to take it all the way. So, because if you think about it, we have this region, and this would be the integral from, say, like 0 to 2 pi, and then this region would be from like pi to 3 pi halves. That's this one. There's nothing that happens here or here, so we don't actually have to worry about those regions. Okay. Anyway, So let's go ahead and get into this one. So we're going to take the integral from 0 to pi halves. I don't know if I said 2 pi or what, but I meant pi halves. If I didn't say that, it's from 0 to pi halves, and this region is from pi to 3 pi halves. Okay, I might have said 2 pi though. Anyway, so 0 to 90 degrees. Okay, and we're going to take 2 times that to get both of them. So it's 1/2 r squared. Now what's nice is our r squared here is just sine of 2 theta, d theta. Okay, so the 1/2 and the 2 cancels. We get the integral from 0 to pi halves of sine 2 theta d theta. Now the integral of sine is going to be negative cosine 2 theta divided by 2 here, because this is like a u sub. If we called d theta equal to u, then our du would be 2 d theta, and so we'd need to put in a 2 and pull out 1/2. That's where that 1/2 is, right here. Okay, just want to point that out. We don't have to use u sub if you recognize that, but I don't want to like make that not clear where those things come from. This was u sub. All right, so we're taking this thing from pi halves to 2. From pi halves to 0, plugging them into this thing. So pi halves, this is negative cosine of just pi. 2 times pi halves is just pi, all over 2, minus negative cosine of 0 over 2. All right, so cosine of pi is -1. A negative and a negative makes a positive, so that's going to be 1/2. Plus cosine of 0 is 1 over 2, 1/2. So we get 0. We get 1. So the area of each one of these then is 1/2. Okay. Now, I just want to point this out is that we do need to be aware that when we are integrating these things, we should just whenever possible, I break them into smaller regions just to avoid any potential like overlap issues. So if we look at this again, if we take this from 0 to pi halves of our let's see, 1/2 sine 2x dx. Okay. Oh, I did the wrong slash, I think. There we go. All right, so notice we get 1/2 for this region. Now, if we were to take this until 3 pi halves, then we end up with kind of an issue here. So from 0 to 3 pi halves, we're just getting pi halves. And the reason for this is if we think about sine of 2x, okay? Let's think about it here. From 0 to pi halves, we have this region here. And from our pi halves to pi, it's negative. So essentially it kind of cuts it out. And the reason it's cutting it out is because technically speaking, what this one is integrating is just our r equals sine 2 theta. So it's actually taking this here. So it's taking 1/2 and it's taking 1/2 here, because when I'm plugging this into my integral, it doesn't recognize that I'm strictly talking about the square root squared. So if I had to do it, maybe I would do like absolute value, and then maybe it would give it correctly. So, but notice in this case, it's now saying it's 1/2, so it's adding this one, and that one. So again, this is what I'm talking about, why we need to break this up, is that when we're doing this, if we look back at what we are integrating, we're basically dealing with this sine 2x here, okay? And so on our region from 0 to pi halves, it is all positive, so we're good there. That would be a area. But if we were to take it from 0 to pi, it would give us back a 0. And if we do it from 0 to 3 pi halves, which is what our whole thing is over, we get a positive 1/2, a positive 1/2, and a negative 1/2, so that's why we get 1/2. And so that's why it's important to, first of all, recognize the function you are integrating. So I always like to think about this function sine 2x as what is it? Make sure it's always positive, because as a reminder, the area and the definite integral are not exactly the same. They are similar. They are only the same when our function is always positive. So again, we're basically just finding this region and that region, which is going to be our 1. Okay, so again, just want to point stuff like that out. Okay, so our area here is 1. Find the area of the region bound by the curve r equals 4 plus 3 sine theta. So let's go ahead and graph that. R equals 4 plus 3 sine theta. All right, so we have this shape here. Okay, so we want to find this region. So again, same idea here. Basically, we want to break it up as much as we can. There's a symmetry along this axis right here. So if we just do it on this side and then this side, you know, or so this side or this side, and then just double it, then we'll get it. So let's go ahead and paste this in. Okay, so again, what I'm doing here is I'm just taking 1/2 of it. Now it's symmetric along what would have been what we call the y-axis. It's right there. Okay, so if we were in x's and y's. So if we think about this, we are taking it from here to here. That was terrible drawing. Let's try it better with a line. So we're taking this, and we're taking it all the way around. Okay, so if we think about that, this is like saying from 3 pi halves to pi halves. Problem with that is basically that would then describe this to here. And if I want to describe from here to here, then actually it's not 3 pi halves. It would be something like negative pi halves to pi halves. I mean, obviously we could take it from pi halves, so from here until 3 pi halves if we want as well to find this left-hand region. It doesn't really matter. But I'm going to take it from integral from negative pi halves down here until here. And we're going to take it over that. Okay, so we're taking this thing, and it's still 1/2 r squared. So that is 4 plus 3 sine theta squared d theta. All right, so let's clean this up a little bit. We have the integral from negative pi halves of 1/2 times 16 plus 1224 sine theta plus sine squared theta times 9 d theta. All right, so we have this thing here. I'm going to go ahead and actually pull this 1/2 out, because even though this 1/2 works here, it doesn't actually work here, so it's not going to make my life any better. So I'm going to pull it out. Now, again, just like in our previous one, it is worth noting, like, what does our actual function that we're integrating, what's it look like? So we're taking 16 plus 24 sine theta, or x here, plus 9 sine x, sine squared x, something like that. Okay, so we want to take it from, in this case, negative pi over 2 is my x, something like that. So if we're taking it from here until x equals pi halves here, then our function here is always positive, so we're okay. I mean, realistically speaking, it's always positive anyway, but it's worth noting that it's positive over the region we care about. Okay, so let's go ahead and it's not undefined at any point along that. That's also important for us. Okay, so we have, this is a quadratic in form. This is 9 sine squared theta plus 24 sine theta plus 16 d theta. And basically, if we think about this thing, we have a quadratic in form, but it doesn't actually matter for us because we are going to just integrate each individual term. That's going to be easier. But I just want to point out it is quadratic in form. It goes back into this. And so it's always worth mentioning when you recognize things as quadratic in form, you should notice them when you see them, just because you want to keep your eye out for those, because a lot of times we run into things that maybe we need to know that about it. All right. So that means that this is essentially 9/2 sine squared theta's integral plus 12 sine theta's integral plus 8 integral. And these are all d thetas. So these ones are easy enough to integrate. This one here, this sine squared, we don't really want it as a squared. We want to go to our trig identities. So as a reminder, this is a half angle kind of problem. So let's take a look at our half angles. So if we have sine or cosine to some even power, we're going to go to our half angle. So let's zoom in a little bit. Sine squared is 1/2 1 minus cosine 2 theta. So that's what we're going to use to integrate this one. So the other ones are easy enough. This is going to be 9/2 times the integral of 1/2 times 1 minus cosine 2 theta plus, so again, that's our sine squared, plus the integral of sine is going to be negative cosine, so it's negative 12 cosine theta plus 8 theta. That's what we have here. So we'll just keep those in mind. We're going to deal with this over here. So this would be 9/4 times the integral of 1 minus 9/4 times the integral of cosine 2 theta. Again, this 9/4 is in each of them, and so I pulled this 1/2 out to make that 9/4, and then I can split these two as two integrals as well. So we end up with 9/4 theta minus 9/4. The integral of cosine is going to be sine here, 2 theta, and then it's over 2. So again, it's another one of those u sub situations. And then this is going to be minus 12 cosine. Let's write that cosine a little bit better. 12 cosine theta plus 8 theta. And we're taking this from pi halves, negative pi halves. Okay, now I know that this and this can actually go together, and so we might as well do that here. This would be 32 over 4 plus 9 over 4 is going to be 41 over 4 theta minus 9/4. I might as well simplify that a little bit too. This will be 9/8 sine 2 theta minus 12 cosine theta, and again we're taking it from pi halves to negative pi halves. Alrighty, so plugging in pi halves, we get 41 over 4 times pi over 2 minus 9 over 8 sine of pi. Sine of pi here would be 0 minus 12 times cosine of pi halves, which would also be 0. Then we say minus negative pi halves times this thing would be negative 41 over 4 times pi halves. The negative's here technically, but whatever. Now minus 9/8 times sine of pi again, in this case sine of negative pi, is going to be the same thing as sine of pi, which is 0, minus 12 times cosine of negative pi halves is also 0. Okay, so these don't matter, and we just have 41 pi over 8 plus 41 pi over 8, which is going to be 82 over 8. They're both divisible, pi. They're both divisible by 2, so that would be 41 over 4 pi. Okay, now keep in mind that what we have found is this half right here. So we just found this half. If we want to do the whole thing, I should have done 2 in front, but I didn't this time. Don't ask me why. Sometimes I just don't do that. So this is for half of it. So that means that it's going back to our 82 pi over 4 for the full thing. But that actually is going to be, so 2 times this, again, is going to be for this thing. But this is both divisible by 2, so this goes to 41 over 2 pi. This is our area of the whole region. Okay, so let's take a look at this thing again on our integral, just to double check that this makes sense. If we go to functions, integration from negative pi over 2 to pi over 2 of our 1/2 times 4 plus 3 sine theta, I'll just call it x squared dx. Okay, we get this. This is half of it. Let's take a look at our half and make sure that that half works out. So 41 over 4 times pi is that thing, and then we double it. So if we had doubled it from the beginning, then we would have ended up with our 64 directly, which is our 41 over 2 pi. Okay, so that checks out. All right. Okay, so for arc length, recall that a rectangular and polar coordinates are related by the equations x is r cosine theta, y is r sine theta. Now, if you recognize, that's basically a parametric. We are converting kind of x's into something else and y into those same variables. So the parametric equation, if we want to convert them just into theta, r, as a reminder, is f of theta. So essentially we can then write x in terms of theta only, which is parametric, and y in terms of theta only, parametric. So essentially we're going to use some concepts of parametric with some concept of our polar, but essentially the reason why we need it in terms of, quote, parametric is just to derive this formula. So suffice to say, it's derived that way. If you want to check it out, obviously there are tons of things on that, I'm sure. The book probably talks about it as well, but I'm not going to waste time with it. I'm going to just focus on using it. So here is our arc length. Our length is the integral from a to b square root r squared instead of r1 plus our y prime squared. Well, in this case it's dr d theta squared, but anyway, so we will go ahead and try out something with this. Okay, so find the length of the portion of the curve shown in blue. Okay, so first of all, we need to think about, this is our curve from it's r equals theta plus 2, and so we need to think about where we're integrating this along. So if we think about this, we start here. Our angle here would be 0. Pi halves, pi, 3 pi halves, 2 pi, 5 pi halves, 3 pi. So it's to 3 pi. So we're going to take this integral from 0 to 3 pi of our square root r squared, which would be theta plus 2 squared, plus, now if we take a look at r prime is just going to be 1, so that would be plus 1 squared d theta. Now, if I were to distribute that, that's kind of the first thing I'm thinking. If you distribute this thing, we have something like theta squared plus 4 theta plus 4 plus 1. But this gives us a quadratic that's not actually factorable. So, you know, if we got something that was like x squared plus 4, or excuse me, theta squared plus 4 theta plus 4, then obviously that would have been squared. Square root would have canceled. But this plus 1 is problematic. So we can't use that. So instead, in order to deal with these square roots, we need to think about our inverse trig substitution here. This is a something squared plus some constant squared, in this case like a 1. And so the plus is going to be our tangent. So as a reminder, we had like x equals a tangent theta. when we had something that was like a squared plus x squared. So we're going to use that logic here. This is our a, so maybe we should rewrite it. This is the square root of 1 squared plus theta plus 2 squared. This is what we have here, and so this is our a, this is our x. So we're going to use that as our substitution. So we have x, which is theta plus 2, is equal to a 1 tangent theta. All right, so if we think about our triangle, we have tangent is opposite theta plus 2 over adjacent 1, and this would be square root of 1 plus theta plus 2 squared. Okay, so if we then solve for theta here, theta equals tangent theta minus 2, and derive this thing. I don't really have to, but whatever. So here's the problem. I'm using thetas. I shouldn't use theta. Instead of calling it theta, let's just call it some other thing, like x. Okay, because since we're in thetas, that would get very confusing very quickly. So rather than doing that, okay, we're going to call them x's. All right. So here. All right, so our d theta is equal to tangent x minus 2's derivative. So the derivative of tangent x is going to be secant squared x, and that's gone, and so dx. Okay, so we are again taking this integral from 0 to 3 pi. So we have something to convert our d thetas into, and we have something that we can convert our like this stuff into. Okay, so that's going to make our lives a lot better. We have the integral from 0 to 3 pi square root of 1 squared, which is just 1, don't really need to write that, plus theta plus 2 is our tangent, so that would be tangent x squared. Okay. Now, d theta is just going to be secant squared x dx. Okay, so, oh no, we are running into that dreaded secant cube that I run into all the time. I don't know why I write problems like this. Why do I hate myself? Anyway, maybe because these curves end up being nice, but whatever. I can already see this is a secant squared. So square root secant squared x. Darn, changing thetas into x's here. Okay, and this would be secant squared x dx. Now, these bounds of integration have technically changed because we have changed it, so I'm not going to write them any further. I'll come back to them. Okay, so this cancels here, and we end up with the integral of our secant cubed x dx, but as we know, this one, I mean, at a certain point, when can we just go to the books tables? I mean, I'm sure the books tables actually has them, but oh well. We'll go ahead and go through it again because it can't hurt to see this one. So, for the millionth time. All right, secant x, secant squared x dx. I'm going to leave it like that because, again, we're going to do integration by parts. So uv minus integral v du, where our u here is secant x, our dv is going to be secant squared x. We're going to derive this thing, so du is equal to secant x tangent x dx. And our v, oh no, I'll just erase it then. Our v is going to be tangent x. This should have been a dx as well there. Doesn't matter. Okay. So, the integral of this, uv, that's going to be secant x tangent x. Okay. Minus the integral of secant x tangent x. secant x. Let's write that a little bit better, and we'll actually write it in the proper order. I was just doing duv, but let's do v first. Tangent x times du, which would be secant x tangent x dx. Okay, so what we end up here with is, this is a tangent squared, so integral, so this is secant x tangent x, minus the integral of tangent squared x secant x dx. Now, tangent squared x, as a reminder, going to our Pythagorean identity, that's going to be secant squared minus 1. So we have secant x tangent x minus the integral of secant x minus 1, secant squared x minus 1, times secant x dx. And that means that we can distribute this, and we get secant x tangent x minus the integral of secant cubed x. Now, minus a negative gives us plus the integral of secant x. I'm splitting these simultaneously to distributing it, because as a reminder, this is all equal to the integral that we're trying to find, secant cubed x. So this is the same thing. We're going to add it over, and we get secant x tangent x plus the integral of secant x. Now that's going to be plus our natural log of absolute value. So as a reminder, this one's one of those ones that has multiple. I'm going to go ahead and pull it up. Integral of secant x. So we have a couple ways to think about it, either this way or this way or this way or these. I personally tend to use this one, but technically speaking, you can do whichever one you want. I'm going to stick with this one, so I just want to remind you of that one. So ln secant x plus tangent x. Alrighty, and so that's the integral here and that, and this is all equal to 2 integral secant cubed x. So I'm trying to find secant cubed x. I'm going to divide everything by 2, and we get secant x tangent x plus natural log secant x plus tangent x over 2, and this is equal to our integral. Now, the problem here is that this thing here is in terms of x, and as a reminder, we wanted them in our thetas that we were originally talking about. So let's go ahead and pull this thing down here. I wanted to just select multiple, thank you. We'll Control C a few times since Smart Notebook hates Control C for some reason. All right, so we're going to use this thing here. All right. So secant of x is 1 over cosine. Cosine is adjacent over hypotenuse, so it's hypotenuse over adjacent. So that is going to be the square root of 1 plus theta plus 2 squared times tangent. Tangent is just going to be theta plus 2 plus natural log of those same things, square root 1 plus theta plus 2 squared plus our theta plus 2 absolute value, and this is all over 2. And we are going to take this now from 3 pi to 0. Okay, so if we plug in 3 pi into this thing, we have the square root of 1 plus 3 pi plus 2 squared times 3 pi plus 2 plus, this is going to be an ugly form, ln absolute value square root 1 plus 3 pi plus 2 squared plus 3 pi plus 2. Don't really need the parentheses there. And this is all over 2, and then it's minus. So, geez, I'm hoping these things cancel out a little bit. Let's think about this one here. So 0, okay, it's not. Okay, fair enough. I will probably extend this down. So let's now look at the 0 portion of it. So it's like minus. Now let's plug in the 0 into this. On the bottom, square root 1 plus 2 squared is 4 times 2 plus natural log absolute value of square root 1 plus 4 plus 2 all over 2. So that cleans up. This one at least is somewhat nice. This one's hideous. Alrighty, so we end up with some exact value, which is disgusting. This thing minus this thing. So square root 5 plus 2, I mean, that's all we can really do with that. So let's clean this up just a tad. We have 3 pi plus 2. I'm just putting this in front of the square root. Square roots 1 plus 3 pi plus 2. I know that I could certainly distribute this thing, but I mean, it really wouldn't make it any better. So I'll just leave it alone. Plus natural log. Now, if we think about this thing here, this is going to be positive, this is positive, and this is positive. We can really drop the absolute value here. We don't actually need it at this stage. So I'm going to drop it. Natural log of the square root of 1 plus 3 pi plus 2 squared plus 3 pi plus 2, okay, minus 2 square roots 5 minus, because the negative distributes to the whole top, minus natural log, and again, same thing as before, we don't need parentheses, natural log of square root 5 plus 2, and this is all over 2. Okay, now that's hideous. That's an absolutely terrible form, but it is what it is. Let's go ahead and see what that value is approximately equal to. So 3 pi plus 2, because that's just terrible. I don't know why I would do that to myself. I know why I do it to you, because, you know, that's the kind of person I am, but why would I do that to myself? Anyway, so square root 1 plus 3 pi plus 2 squared plus 3 pi plus 2. Okay, let's look at this thing here. Okay, that is plus that thing. Good. Minus 2 square roots 5 minus natural log of square root 5 plus 2. That's all of it is divided by 2. So we get 64.119-ish. Now, let's check that integral. Let's make sure we integrated this okay. So functions, because you'd hate to get to the end and not check. Like, why not? Check your answer, especially with an integral this ugly. Though you might just be like, well, it doesn't really matter if I got it right or not. I'm not doing that all over again. Which, fair enough. That's maybe not a great way to think about it, but okay. X plus 2 squared plus 1 dx. And we got the same value. Whew, thank goodness, huh? Though this is an approximation, we like this form down here. This is the good form somehow. That. All right. Anyway. Okay, so now let's talk about tangents. The parametric equation, as a reminder, we did the parametric equation for our arc length, but the parametric equation for our polar curve is x is equal to f of theta cosine theta, and y is f of theta sine theta. So using the same concepts we used in our tangent of a parametric, as a reminder, if we were trying to find dy dx, this was going to be dy dt over dx dt. That's what that thing was. So in our case, we are taking with respect to theta instead of t. And so we're just going to have dy d theta over dx d theta. So if we think about this thing here, that means that if we are integrating our y with respect to theta, we get just this thing's an r, again, as a reminder, kind of like this. Okay, so the derivative of r is dr d theta times sine theta plus the derivative of sine is cosine times r. That's what that is because it's a product rule. Here, same thing, product rule of this one, again, r cosine theta, dr d theta times cosine theta minus, leave r alone, derivative of cosine is negative sign, so that's where that minus comes from. So it's a plus, a negative. All right, so we have this slope of a parametric curve, and again, it follows exactly the same as our slope of a parametric curve in terms of t, but now we're doing it for theta. So again, our polar coordinates are parametric. All right, so let's take a look at an example. Find the slope of the tangent line to the given polar curve at the point specified. So when theta is pi thirds. Okay, so we have something like r equals 2 cosine theta. And we have our theta is pi thirds. This is the point that we care about. And again, as a reminder, this is what we're using here. So I'm going to go ahead and snip it just to make our lives a little bit better and bring it onto the other page. So, oops, let's shrink this since it's obnoxiously large here. Okay, so we're going to use this thing here. So what we need to find is dr d theta, so the derivative of it. So that is r prime. R prime is going to be the derivative of 2 cosine theta is derivative of cosine is negative sine. So it's negative 2 sine theta. All right. So now we're just going to plug all these things into our equation here. So we have negative 2 sine theta times sine theta plus r, which in our case, what is our r? 2 cosine theta. 2 cosine theta times cosine theta. And this is all over our negative 2 sine theta times cosine theta minus r, which is again 2 cosine theta times sine theta. Okay, so we want to know this thing at the point theta equals pi thirds. All right, so I'll clean this up a little bit though. We have negative 2 sine squared theta plus 2 cosine squared theta, which if we think about that, this is all over our negative 2 sine theta cosine theta, okay, minus 2 sine theta cosine theta. So we can clean this up just a little bit. Okay, so essentially we can factor out a negative 2 out of the top. That would leave behind sine squared theta minus cosine squared theta. So it's not quite the 1 that we're looking for. So that's too bad, but such is life. Okay, I mean, we could certainly clean this up a little bit if we wanted, but it's just worth noting that when it's in this form, it's easy to go, oh, well, that's just 1. So it's negative 2 plus 2 or something like that, but it's not. Now, negative 2 minus 2, but they're like terms here, so that's going to be minus 4 sine theta cosine theta. So the negative 2 makes a 1, and this will make a 2. So we have sine squared theta minus cosine squared theta over 2 sine theta cosine theta. And this is our derivative, basically, our dy dx concept here, okay? This is our derivative. And now we want to know when theta equals our pi thirds. So, as a reminder, if we look at our unit circle, it might be helpful for you to see this since pi thirds are maybe not as obvious to you guys, so I just want to make sure. I feel like sometimes people just jump through it like, oh yeah, it's this and this. And it's like, okay, wait, hold up, let me remember. Okay, so we're doing sine squared of pi thirds. Sine is square root 3 over 2 squared. So square root 3 over 2 squared minus our cosine squared of that thing. So cosine is 1/2 squared over 2 times our sine, which was square root 3 over 2, times our cosine, 1/2. Okay, so this 2 and this 2 would cancel. We still have a 2 left, but
Really some of it would cancel. And on top here, we'd have 3 over 4, because it's squared. Square root of 3 squared is 3, 2 squared is 4, minus 1/4 over our square root 3 over 2. So this is going to give us 2/4 over square root 3 over 2, which is really 1/2 times 2 over square root 3. These 2's cancel and we get 1 over square root 3, which if you want to rationalize it, if you'd like to, that would be square root 3 over 3. But that is our slope at that point. And we can double check that that's like believable, I suppose, if we graph this thing. If we have our r equals 2 cosine theta. Okay. Let's go back. That's what this thing here is. And we want to know the slope at some point here. So the slope at theta is pi thirds. So here, I don't know if we can actually graph this. Theta equals pi over 3. No, it doesn't like it. That's okay. Too bad. But pi thirds here is going to be right here. So it's this point right there. Okay, so that would be here. And it's positive. At least we can tell that it's positive. Okay, so square root 3 over 3 is positive. So that at least reads okay. It's not great, but such is life. It's right there. Okay, so that has been our calculus in polar coordinates. So again, much like parametric, what really is hard about it is the same thing that's hard about calculus in general, is just we run into integrals that are tough to integrate sometimes. That's really what makes it hard. The polar coordinates or the parametric is not necessarily a problem. So again, we shouldn't be afraid of using polar or parametric when it would make our lives easier. So in this case, polar a lot of times is just much easier to describe the curves than in terms of x, y, so we might as well write them in polar. Because again, that would then just mean that the only hard part of this is the integration, which would be hard either way. So thanks for watching.